Good day, everyone. This is Chris of the Ancient Scholar. Today what I'd like to do is I'd like to cover a couple of questions and really talk about using analysis and critical thinking to work through questions to make them a little simpler, a little easier to understand and to derive the answer, if you will, when you're really not sure what's going on. And these are a couple of questions that I was actually asked this morning by one of my friends. I think he's looking at CLEPing a chemistry course. I think the CLEP test he was studying and did some practice questions, had some questions about what was going on. So with that, we'll go ahead and discuss some techniques that we can use to kind of zero in on an answer when we have multiple options available. So the first question goes something like this. I have some substance. It can be whatever. It's an acid. Let's say it's acidic, whatever, organic, some sort of organic molecule, has a pKa value of 4.1 and a pH of 4.1. That's currently. And then the question goes on to ask, what is the approximate pH what is the approximate pH value if the pH is 1,000 times higher or more concentrated or stronger than the original pH of 4.1? And then it goes on to say A. You can select one of the four. A is 3, B is 2, C is 1, and D is 0. So I just went ahead and wrote the problem down so everybody can see that. It's a pH. There's my pKa value. My answers. And let's go ahead and figure this out. Okay, so first of all, the pH and the pKa are the same. And here's the interesting thing about this question. They've given you more information than you really need. In a lot of questions, this doesn't necessarily even have to do with chemistry, but a lot of questions will give you more information than you really need. You look at that and you go, oh gosh, what's pKa? It's a Ka value, and that's a dissociation constant, and P means that it's a logarithm, and oh my goodness. It's not really relevant, actually, to this question. It just says, look, I have a substance, has a pH of 4.1. What is the approximate pH of the substance if the pH is 1,000 times higher? Well, if we remember, looking at this question, if we remember, we can do a lot of things to figure this out. We can do a lot of math, involves scientific notation, or we can look at really what they're asking. They're saying, hey, I take something at a pH of 4.1, I make it 1,000 times more concentrated, what will the approximate pH of that new substance be? And, the pH and pKa are the same, so we don't have any craziness there. So the way I look at it is I got to go back and I say, okay, what is pH? Well, pH is a logarithmic scale. It's based on the metric system. It's based on powers of 10. Okay, so what I do is I start at 4.1, and I just put a 0 there, okay? And I say, okay, I'm going to start at 4.1, that's 0. And then I'm going to ask myself, well, what would be 10 times stronger or more concentrated, 10 times more hydrogen or hydronium ions than 4.1? Well, that would be 3.1, okay? My pH is decreased by 1, and that's 10 times the concentration, because this is a logarithm. So it's base 10. Well, the logarithms that we deal with in chemistry primarily are base 10, specifically the pH. And then I ask myself, well, let's say I decrease the pH one more, and I go from 3.1 to 2.1. Well, that's another 10 times or 100 times more concentrated. And then I go, well, let's say I go from 2.1 down to 1.1. Well, that's 10. So 4.1 to 3.1 is 10 times. 3.1 to 2.1 is 100 times. 2.1 to 1.1 would be 1,000 times. And there we have arrived at our answer, 1.1. No advanced math, no craziness, just simply looking at it analytically and realizing how a logarithm works. So then I go back to my question, and all I have to do is choose the answer that closest approximation to the answer that I derived, and that would be C here. pH of 1 is going to be approximately 1,000 times more concentrated or higher than a pH of 4.1. So again, not having to really use any advanced math, and really all it is just understanding what a logarithm is and understanding what the relevant information to the question is. Okay, let's do another one here. So this is another question that he had, and the question goes like this. Why are 2p electrons in fluorine at higher energy levels than 2p electrons in oxygen? Okay, and the answers are A, relativistic effects, B, penetration or probability density, C, electron repulsion, or D, none of the above. And this is kind of a tricky one because there's always a chance it could be none of them, and I think these kinds of answers add a little more confusion to the mix. So let me go ahead and show you guys the question and answers here. All right. So 2p electron energies are electrons in 2p orbitals in fluorine are higher energy than 2p electrons in oxygen. Why? It's got to be one of these four rather. Okay, so in this instance, let's see if we can eliminate some things. Well, let's go ahead and start at A, relativistic effects. Do relativistic effects occur in atoms, in electrons? And the answer is yes, absolutely they do occur. However, are they particularly relevant in 2p orbitals? And the answer to that is not particularly relevant, certainly not in general chemistry. Where do relativistic effects become relevant? Well, when we talk about transition metals, specifically, your higher d orbitals, and this is actually the relativistic effects of the electrons. That's one of the issues that we deal with in metals that are liquid at room temperature, like mercury, and a couple of other metals that are liquid fairly close to room or body temperature. So relativistic effects are relevant, but not particularly relevant when you talk about 2p. You're only talking about the second shell of electrons. So you can pretty much say, hey, I'm not really buying relativistic effects. And then we go on to B, penetration and probability density. And if we remember, what type of orbital has the highest probability density closest to the nucleus? Well, s orbitals, in fact, penetrate closer to the nucleus. So an s orbital, an electron in an s orbital, is going to spend more time closer to the nucleus, and we would expect the energy to be higher or lower in an s orbital. Well, we should expect lower energies. Remember, the closer the electron is, to the nucleus, so the more probability density it has closer to the nucleus, the lower the energy. Okay, the further away the electron is, the higher the energy. Now, in fluorine and oxygen, they're both 2p orbitals, but we can also get rid of penetration and probability density simply because we're talking about p orbitals and not s orbitals. And then it's down to electron repulsion or none of the above. What's going on here? How can I rule one in or can I rule one out? Well, it's going to be hard to rule none of the above out, but what we can do is we can take a look at the electron configuration of these two atoms. So oxygen is atomic number of 8. So what I do is I simply write the electron configuration for oxygen out, and we'll compare that to the electron configuration of fluorine. So oxygen's 8, so I have 1s2, it's 2 electrons in the 1s, 2s2, 2 electrons in 2s, and then 2p4, 4 electrons in the 2p orbitals rather. And then I'll compare that to fluorine, which has an atomic number of 9. The configuration is 1s2, 2s2, 2p5. So what do I have going on here? Well, I have one additional electron in the 2p orbitals in fluorine than I do oxygen. So if I have more electrons in those orbitals, what's going on? Well, think about what happens when I put electrons close to one another. There's electron repulsion. They repel, and they don't necessarily feel the full the full force of attraction, if you will, from the nucleus, because there's some repulsion going on, because there are more electrons in fluorine. So the answer then to this question would be electronic repulsion, simply because there are more electrons in the 2p orbital of fluorine, and electron repulsion will be the most relevant thing going on there. I'll go ahead and show you guys that. Okay, I'm going to go ahead and cut off here, and maybe I'll do a couple more questions in the future. As always, thanks for hanging in there.